This is video 29 in the lecture on the design of reinforced concrete beams. This lecture deals with the behavior of a cross-section in shear and torsion. We will first talk about the cross-section and the resistance against shear, but without additional reinforcement. Afterwards, we will see what the stirrups will contribute, how they will contribute. We will give you a calculation method for shear and torsion, and we will end with two examples of shear and torsion reinforcement. Suppose we have a beam which is loaded by two local loads. Then we see that in the middle the cracks are vertical or almost vertical. Once you go to the support, the cracks are more and more inclined. If we look at the bending moment, then we see that the bending moment is constant in the middle between the two loads. So these cracks are cracks due to bending. On the other hand, when the cracks are inclined, these are cracks induced by shear force, because that's the shear force diagram. Those cracks in shear force, they are there in suddenly, so there's no warning system. So a failure by shear force is really a brittle failure, so it is ULS situation. You do not handle shear force in SLS. Suppose we have a beam in a material, homogeneous, isotropic, continu, and elastic and non-cracked section. We look at the neutral axis and we take one portion out of it, a portion with a length dx. We have a bending moment in front of it and a bending moment at the back of it. We see that for the section in compression, the total compression force is N, and after the section it is N plus dN, the increment. Now, because of equilibrium, the total or the net compression force is of course N plus dN minus N is dN, and it must be in equilibrium with the horizontal force, which is a shear force at the level of the neutral axis, multiplied by the cross section B times dx. B is the width of the section. So this is just a translation equilibrium. We see that the tau and A equals dN accent divided by B dx. So now let's look, if you take the bending moment, then the bending moment is of course the normal force times its lever arm. If you differentiate it, you have dm is dn times z plus dz times n, but dz is here in this case 0. There is no increment or of the lever arm in function of x. So dn over dn can be replaced by dm over z. So dn, we replace it by dm over z. But now we got dm over dx, and we know that this is the shear force. So the shear stress, tau, at the level of the neutral axis for this kind of material, non-cracked section, is the shear force divided by the cross-section B times Z. For a non-cracked cross-section, we can use Juravsky for a rectangular section relative to the neutral axis. We know that then that the shear stress tau xa equals the shear force times Sz divided by Biz. And Sz is equal, if you take the part above the neutral axis, is of course the cross-section B times h divided by 2 multiplied by the distance to the neutral axis. And the moment of inertia is then, of course, bh to the power third divided by 12. And if you now use this formula, then you see that the shear stress equals V times this divided by the width and divided by Ez, and we have 1.5 V divided by BH. Now let's have a look at a rectangular cross section. The green part is the section in compression. Now we are just going to calculate the shear stress in function of the coordinate Z. Z is 0 at neutral axis and it's h over 2 at the most compressed fiber. You take the moment of inertia, bh to the third divided by 12, S equals Z plus h over 2 minus Z divided by 2, or S is Z over 2 plus h over 4. This is here the point of gravity of the section in compression relative to Z. And the S equals then the total area, green area, times his lever arm. Then we can substitute the different elements and we have a formula of the static moment of inertia in function of the coordinate Z. Of course, when Z is 0, the moment of inertia is 0, and when Z is h over 2, we have the maximum value. The shear stress is then Vs divided by Eb. If we just use the formula standing here, then this is the expression of the shear stress in function of Z. And you see immediately this is a parabolic curve. When the shear stress is 0, this is only happening when Z is equal to h over 2 or minus h over 2. So at the top it's 0 and at the bottom it's 0, and it's maximum when Z is 0, and we arrive again at the same formula that we've seen before. So if you have a beam uniformly loaded or loaded by uniform distributed load, then you see that the shear stress is varying in the cross section with a maximum at the neutral axis. And this is, in an ideal case, the formula. Now, if you look at the mean shear stress for a rectangular cracked cross section, because this was for a non-cracked cross section, if you look at it for a cracked cross section, then it can be demonstrated, it can be proven in tests that the shear force, the mean shear stress, is equal to the shear force divided by B times Z. And Z can be taken as 0.9 times the effective depth of the section. So instead of getting blocked by this figure, by this evolution of the shear stress in the cross section, we can use a mean shear stress, which is the shear force divided by Bz. Now look at the mechanism of shear resistance. We have 4 parts. The first part, this is the shear crack, and it's typical shear crack. Now, at the bottom, the shear crack is open, and on the top, it's closed. In zone A, we are in a compression zone of the beam, so it's uncracked concrete in compression. A bit further on, the tensile stress in concrete is not exceeded, so we have a resistance done by the tensile stresses in the concrete. If you go to portion C, then the concrete is cracked. There is no resistance from the tensile stresses, but there is a granulate interlocking of the concrete. Friction, it's kind of friction. And then when we arrive at the longitudinal reinforcement, bending reinforcement, then we have a dowel action, which gives you also a resistance to shear force. So the total resistance to shear force is something that is achieved by those four systems. It means that shear loading bearing capacity of a beam without shear reinforcement depends on the concrete class because of the tensile stresses and the compressive stress, the main reinforcement ratio because of zone D, width and depth of the cross section, and of course the actual force if there is an additional actual force in the section. Experimentally, we have arrived the following formula. This is the design value of the shear resistance of a beam without shear reinforcement. The C is for concrete. So it's the resistance to shear without shear reinforcement. It is of course this is of course the cross section BV times D. BW is in fact the width of the section, but it's the smallest width of a section. If the width of the section is varying along the vertical axis, then BW is the smallest. It's BW multiplied by the shear stress, which is here between brackets, between big brackets. First, it's CRDC, it's the safety coefficient, the material coefficient. It's 0.18 divided by the material coefficient of concrete, which is 1.5. K factor is a scale factor. It's 1 plus square root of 200 divided by D, and D in millimeter. And rho L, it's the density of the longitudinal reinforcement, and it's defined as ASL divided by BWD, must always be smaller than 2%, so you cannot put here a value which is bigger than 2%. Then we have the factor K1. K1 is 0.15, and sigma CP is the net compressive stress, external compressive stress in the section, which is the external compression force divided by the cross section of the beam. And it must always be smaller than 1/5 of FCD. So if this value is bigger than 0.2 FCD, you must replace it by 0.2 FCD. This term is the contribution to the resistance against shear force of the compression force, external compression force. FCK, of course, is the quality of the concrete. There is also a minimum value, which is BWD times nu minimum, plus again K1 sigma CP, and the minimum is a function of the concrete quality and the K factor, which is defined here. So the real design value of the shear resistance of a beam without shear reinforcement is the maximum of those two. Is the maximum of VRDC and VRDC min. Now we have seen that rho L is there, the density of the reinforcement defined as the cross section of reinforcement divided by BWD. And this density of reinforcement is defined if you have a section where VED is taken, which is here, the dotted line at A, then the rho L is calculated at this point. So it's at 45 degrees, let's say at a distance D, but the distance D towards the decreasing bending moment. You can only take this longitudinal reinforcement into account, which is at least D plus anchorage length LBD separated from the section where you calculate the shear. So to repeat, at the position where you calculate the shear, the rho SL, the density of the reinforcement, of the longitudinal reinforcement, must be calculated only for the reinforcement with which is extending D plus LBD from the point of your section, plus it must be at a distance D in the direction of the decreasing bending moment. We can now calculate the contribution of the concrete to the resistance of a cross-section to shear. See you in next lecture.